In this video, I will discuss magnetic dipoles. The two ways that we typically describe magnetic dipoles. One is a magnet, and we have the North Pole, we have the South Pole, and we know the magnetic field created by the magnet points away from the North Pole, and then it wraps around the magnet, and as you're approaching the South Pole, the magnetic field points towards the South Pole. Now, this is one way to think about magnetic dipoles. The other way, at the end of the day, when we have a magnetic effect, what we really have is moving charges. Even though we don't really think of a magnet as moving charges, the way that magnetism works, we do have moving charges inside the magnet. Now, another way that's a little bit more clear to us that charges are moving is if you have a wire connected to a battery and you make the wire into a circular loop and you have a current flowing, then of course we think of the wire containing moving charges. And we have seen if the current is flowing in this way, so this is the side of the wire that is the closest to us, and let's say this is the conventional current, then we know that the magnetic field is gonna point away here, and then it will curl around the loop, and it will point towards the center of the loop if you are on this side. Now, these are the two ways with which you can think about magnetic dipoles. Now, when we work with theory, with magnetic field theory, then we don't really use the idea of having a magnet. We instead discuss currents. So that's why you will see almost all the time all the discussion in the chapter about magnetic fields in matter is really about tiny currents. And at the end of the day, as I said before, even when you have a permanent magnet, what it really is going on is that you have charges moving inside the magnet. Now, I want to mention some important properties of magnetic dipoles. For the magnet on the axis, so let's say parallel to the axis, I know that if you are sufficiently far away from your magnet, the strength of the magnetic field will be mu naught over 4 pi times 2 times the magnetic dipole moment over r cubed. Okay, and this is valid if you have r much greater than s, where s, this is, let's say, the length of the magnet or the size of the magnet. And r is the distance from the center of the magnet to the observation location. Now, for a loop, on the loop's axis, on the axis, we have mu naught Now, this is exact on the loop's axis. By axis, I mean the line that is perpendicular to the plane of the loop and passes through the center. Now, if I make the similar assumption with what I did for the magnet, then Z is going to be much greater than R, and this means this term will be negligible here. So in that case, this becomes mu naught 2 over Z cubed. Now the important thing here, okay, and this is true if Z is much greater than R. At the end of the day, this is a similar assumption with the one I had for the magnet. Now the important thing is to pay attention to the distance dependence. Here I have 1 over R cubed, here I have 1 over Z cubed, and R and Z, it's the same, it's just different notation. At the end of the day, they are all about the distance from the center, either the magnet or the loop. So both of these have a distance dependence of 1 over R cubed. And this is an important feature of magnetic dipoles. The magnetic field of a magnetic dipole will need to be proportional to 1 over R cubed. Now, as I said before, in the chapter where we will see how magnetic fields behave inside matter, all the discussion will be about the currents. Now, in this example, okay, I used example where the wire had the shape of a circular loop. It doesn't have to be that way. You may see as you read the textbook that we have like a rectangular wire, or we have a different shape wire. At the end of the day, the important thing is that you have a current flowing in a closed loop, and you get a magnetic field that is 1 over R cubed. And I do want to remind you also for this chapter where we will see how magnetic fields behave inside matter. Okay, in electrostatics, and when we talked about electric fields in matter, we did have the presence of electric charges. Right, you can charge an insulator, you can place some charges. Because as far as we know, with magnetism there are no magnetic monopoles. You will not see any magnetic charges, if you want. Okay, everything that you will see will be about dipoles, magnetic dipoles, which we think of as currents flowing in loops.